So in today's lecture, we'll be practically executing the simple linear regression programs and a few concepts and a few important notes here and there, and then we can switch over to multiple linear regression. So we have already seen about the gradient descent algorithm. Now a kind of simplification for this algorithm during computation that I will explain. So in gradient, excuse me. So in gradient descent algorithm, we have seen that we need to repeat theta j is equal to theta j minus alpha d by d theta j of j of theta 0 and theta 1. Now, instead of theta j, where j can be either 0 or 1, okay, and simultaneous update of theta j. So, what we need to understand here is we can simplify this derivative because we know that j of theta 0 and theta 1 is nothing but 1 by 2m summation I from 0 to m y hat minus y for each y. But y hat is nothing but h of x, and this h of x is nothing but theta 0 plus theta 1 x for each x. So instead of y hat, what we will write is 1 upon 2m summation I is equal to 0 to m theta 0 plus theta 1 x. Okay, so this is the simplified form, and if we substitute this over here in place of j of theta 0 theta 1, we can write it as let us write it as h of xi minus y. Okay, where h of xi is this part. Now, when we solve the derivative, when we want to solve the derivative, let us take j as 0 first, which will become equal to theta 0 minus alpha. Now, if you know a bit of calculus, you can solve it. I'll write the direct answer. Now, this is a square actually over here. Okay. So this square, when we take derivative of x square, it becomes 2x space problem. When we take derivative of x square, it is nothing but 2x d by dx of x. So initially power of x was 2. Now power of x is 1. So d by dx of x itself becomes 1. This whole thing. So this will become just 2x into 1, which is 2x. And suppose outside this 2x, we have a half. Then what happens? This and this half gets cancelled. So that is what will happen over here. Since whenever we take derivative of cost function, um, a small correction in the above formula. We are writing cost function, right? So it should be 1 upon 2m summation I is equal to 0 to m. And this has this one. Okay. So here we have that 2m. Please make a change in the formula. This is what should come because this whole thing involves the cost function. So I've substituted the formula for the expression for j of theta 0, theta 1. Now, when we take the derivative of this 2 will come outside and it will cancel this half. That is why we have a remaining portion of 1 upon m. So further, if we consider for theta 0 only, it will become minus alpha, and this is now the derivative part that I will write. After solving the derivative, what we'll get is 1 upon m summation of I is equal to 1 to m h of xi minus 1. Okay, this is what we'll get after solving the derivative. Now, in the h of x formula, what we have is h of x is equal to theta 0 plus theta 1. With theta 0, we do not have any variable x. There is no x with theta 0. That is why this is the formula. But when we do the derivation for theta 1, that means here we have done it for theta 0. When we do it for theta 1, we'll get an extra term because of this x. I will show you. So theta 0 that we have found out is for theta 1, the formula will turn out to be an additional xi at the end will get multiplied. Okay. So gradient descent this way will help us to find the optimum values of the parameters to reduce the error in the prediction in comparison with the actual values of the output. Now, this is the program in which the gradient descent algorithm has been executed based on the formulas that we have derived, right? So now for this, you need to run such programs in a platform like Jupyter Notebook, which is one of the products that you get on installing the Anaconda platform, or separately you can install Jupyter Notebook, or you can do it in Google Colab as well, which is an online platform run on the cloud in which you don't have to install anything. Or there are different platforms, but such kind of notebook environment is quite easy to execute programs, especially when you're in the learning stage, because cell by cell you can execute. In this particular cell, what you write will be executed separately. And in this cell, whatever you write, you can execute taking reference of the previous cell, and so on can be done. Hence, this is an easy and good environment. So there are certain special libraries in Python that you can make use of. The special libraries in Python are such as pandas, NumPy, sklearn or scikit-learn, matplotlib, Seaborn. These are some popular libraries and many others. Pandas is used for data analytics or holding the data in a data frame and so on. This is numerical Python. Involves arrays in case of Python and different computations, statistics and all. sklearn is used for pre-processing or importing the machine learning models. And it has a synonymous name called as scikit-learn. Now, this sklearn or scikit-learn in terms of development was actually a challenge that was taken up in Google's Summer of Code. And sklearn is a dummy package of scikit-learn. So while installing these libraries, you can use pip, that is Python installation package manager. Pip install whatever library name. You can install it this way through the terminal or in the notebook. If it is not done on the terminal, then you need an exclamation mark saying that it is not an OS level command. These are some conventions. So while installing, you need to install it by the name scikit-learn. But while importing it inside your Jupyter notebook to access the functionality, you need to import it as sklearn. Even while uninstalling this library, if you uninstall using sklearn, which is just a dummy package, it will not actually uninstall the scikit-learn functionality. Hence, you need to install as well as uninstall using the name scikit-learn, but import in your program using the name sklearn. Matplotlib and Seaborn mainly for data visualization, plotting of graphs, and so on. So we'll see these libraries much in detail when we actually execute our machine learning practicals. But for now, this much is sufficient. So here we have imported NumPy as NP. As stands for alias. That means NumPy can be accessed using the word NP as a short form. You can call it NP, NUMP, anything what you want. But conventionally, NP is followed. Then you can have arrays in Python using NumPy. Syntax is this np.array and give a list of the values. So X is the NumPy array representing what? Representing the feature. And Y is the NumPy array. You can say collection of values representing the label. Then this is a user-defined function called as gradient descent. Initial value. Now, how the gradient descent works actually is, it will assume values of θ0 and θ1, any arbitrary value. And from there onwards, it will start to get the optimal value of θ0 and θ1 such that you reach the global optimum point. So initially, let θ0, θ1 be equal to 0. Here θ0, θ1 are called as current values of θ0, θ1, and they are actually called as alpha1, a1 and a0 over here. They are nothing but here θ0 and θ1 respectively. And how long should the gradient descent work? We know that it is a repetition of the computation of theta of j. How many times iterations are indicated by 1000? That means 1000 iterations. And the number of training examples. Usually we denote it by what? M. But here in this program, it is by N, which is nothing but the total number of values in either X or Y. Because the number of X is equal to the number of Y. That means number of values in the, suppose this is our data set, the number of features that are given here should be equal to number of labels. Because if you have an input, you need an output to predict, right? So either length of X or length of Y. Then learning rate, represented by what in our program? By in our theory, that is alpha. Here we are writing learning rate. So for a range of all the iterations, that means from 0 to 1000, that means actually 0, 1, 2, 3, 4, and so on up to 999. For these many number of times, you will predict Y. Y is equal to mx plus c. But we know that here, this a1 of curve and a0 of curve, θ0 and θ1, we know that we can write y predict as h of x, which is nothing but θ0 plus θ1x, isn't it? So our θ0, this is our θ1 and this is our θ0. Y is equal to θ1 into x plus θ0. And this is our hypothesis. This is our hypothesis. I'll just erase some things over here for clarity. Okay. So this is our feature and this is our label. These are nothing but theta 0 and theta 1. Then number of iterations, that means number of repetitions in our gradient descent algorithm. Then this is the number of training examples. In our case, we call it as M, here it is N. Learning rate alpha. Then for so many iterations, we need to first of all compute the hypothesis h of x, that is y pred. Then our cost function is what? We know that our cost function is this one. What we need to do is 1 upon two m. Just a minute. Yeah. So here we are going to do the summation, and we know that we have to take the square in our summation, and we are taking the square of the value, which is nothing but difference between predicted and actual value. So it is 1 upon m, the square of the prediction value. Here actually 2 should come, 2n, in our case 2m. So 1 upon 2 times something. And this is our partial derivative. So if we want to write 1 upon m, we'll actually have to do some modification here when we are computing the partial derivatives, so that automatically this 2 and the 2 from that coming from the derivative gets cancelled. That is why directly it has been written over here. So this 1 upon n in our cost function, because automatically here we are going to cancel it, okay? So that is why directly it has been written. And then we are finding, now we know that one derivative we need to take with respect to theta 0 and one derivative for theta 1 in the formula for theta 0 and theta 1. So we find out the derivatives, and then we know that theta 1 is nothing but theta 1 minus the learning rate alpha into the computed derivative with respect to theta 1. Similarly, theta 0 is nothing but theta 0 minus alpha into the computed derivative. So that is what we have calculated simultaneously, theta 0, theta 1. And then we'll keep on updating. And finally, we'll print theta 0, theta 1, our cost function, and the iteration value at which we are computing. Okay, so same thing what formulas we have learned. We just need to find the y prediction, and then the cost function, and then the gradient descent algorithm. Now, our main focus is what? Gradient descent algorithms execution. Now, in executing gradient descent algorithm, we know that the formula of gradient descent algorithm is theta of j minus alpha of d by d theta of h of x minus y. 1 by 2 summation of this, okay, square, because it is derivative of the cost function. Okay, I'll write it properly for you. We know that our cost function of j of theta 0, theta 1, which I will write like this. And here we have to write about our cost function. So when we write about our cost function, it will be summation of h of x, which is theta 0 plus theta 1 x minus y for every value of y, and it will be the square. So we need this predicted value, that is h of x. Then we'll use that predicted value to compute this entire cost function. And then that entire cost function will substitute in this particular formula to calculate theta 0. That is why I need the predicted value, that is h of x, the cost function, ultimately to calculate thetas in the gradient descent algorithm. So that is what is being done manually. And as you can see, for every iteration, we are printing the values of theta 0, theta 1 cost and iteration. So initially the cost or the error, it is 8900. And then it is reducing. Sometimes it is increasing in between. And then finally, when you go further down for iteration number 271, 275, suppose, for these iterations, you can see cost has reduced 2 point something, has become single digit point something. So this way it will reduce. So this is how it will take. So cost is reducing as iterations are increasing, right? So if we try to plot a graph of, the theta and the cost, the cost is initially high suppose, and this, sorry, not theta over here, but let us plot a graph of cost function against the number of iterations. So as number of iterations increases, the cost function will reduce. And we have seen that it is happening exponentially as per our program as well. So this is the graph of cost against number of iterations. So that was implementation of linear regression manually. Okay. Mainly execution of gradient descent algorithm after computing our hypothesis, our cost, and then implementing that or substituting that in our gradient descent algorithm steps. Now we can implement all of this without remembering any formulas by directly importing the libraries. So here, this is written to execute matplotlib functionality in line with the code. Even if you don't write this, it can work. So here we are importing numpy as np, pandas as pd, matplotlib is the library, and within that library we want the plotting functionality called as pyplot, and we are importing it as plt. Okay. Then plt.c params, this is just to set the figure size. That means whatever graph we plot, it should span across how many rows and how many columns. So this is 20 row size and 10 column size. That means height and width in general. Now read the data. Using pandas, you can read the data stored in CSV files. Now this is a linear regression case wherein the size of your head and brain weight, a relation between them is trying to be established. Linear relation called as linear regression through that. Now, once we read the data, whatever rows and columns are stored in the CSV file. CSV file means comma separated values file, similar to an Excel file or Google spreadsheet. So we'll read these comma separated values and store it in a, this is data is actually, it will has the data type called as data frame. Data frame is nothing but a tabular format consisting of rows and columns. Okay. So this data frame is a 2D structure because it is a tabular structure. So when we print the shape, we'll get the dimensions, some rows into some columns. And this data frame, we are referring to it as data by the data name. Like how we want to refer to the integer value 5, we write a equal to 5. So we are referring to 5 using the variable name a. Similarly, we are referring to the data frame using the variable name data. And data.head means first 5 training examples or first 5 rows of the entire frame will be selected. So these are the first 5. These are the first 5 rows, index starting from 0 to 4, in which we have the gender, the age, range, and the head size and the brain weight. Mainly our head size and our brain weight are the main features in which we are interested. This is our feature and this is our label. So X is the feature, we are taking this particular column of the data frame and write dot values, because this is actually, we are storing it as a NumPy array. When we write some column of the data frame dot values, whatever values are there in that particular column will get stored as an array called as NumPy array. Whenever we write dot values, the column values of the pandas data frame get converted as elements of a NumPy array, which will be stored in X for as feature and Y as label. Then here again, we can okay, so this is again manual way of implementing. Okay, not using all, not exactly automation, but this is also a manual way. See, initially what we did was using gradient descent algorithm, means how the computer finds out. This is the way how it does. Before this, I've also shown you manually how to execute linear regression, in which we find the mean values and then we compute it and all. Means we basically make use of y is equal to mx plus c. What do? We have x and y values. We calculate the mean. After calculating the mean, we will find out the slope, which is the x minus x bar into y minus y bar upon x minus x bar, the whole square. This is our formula for calculating slope. And then we know m, we know x, we know y, we can find out y-intercept. And then for any new x, we have mcx, we can find out y. This is the manual way. This is the program is for doing it the manual way. Okay. So initially we saw the gradient descent computer way. Now we are seeing this particular method, which we use by human beings, how they can solve linear regression. So NumPy library provides the dot mean function, in which you pass the NumPy array, you'll find the mean of the list of those elements. So x bar and y bar is stored over here. And then total number of values, that means total number of training examples, I've told you it is the length of the NumPy array. Then this is our numerator and this is our denominator, right? In our formula to calculate slope. So initialize them to 0. And then what we are going to do is, see, x minus x bar into y minus y bar. And then we have, this is our numerator, and our denominator is what? X minus x bar, the whole square. So our b1 is nothing but our slope, which is nothing but now our numerator upon denominator. And this is what summation, right? So only we are doing plus equal to over here. We are going to sum up we are going to perform the summation by using this loop and doing plus equal to. Just go through the code once. I know you'll have done Python in your first year of engineering, so you all should be familiar with what is happening here. Summation can be done using the loop and adding continuously the values. Because we know that summation is nothing but sum of the elements. And we know that our constant c, we can find it how? We know that y is equal to mx plus c. So c is nothing but y minus mx. Y minus mx. And we can use y, and this is our m, and this is our x. Okay. So performing the manually way by writing a program for it, this is how it will work. And then finally, we can plot it also in this Jupyter notebook using pandas libraries, using matplotlib. The plotting can be done such that now, which is our independent feature? It is the head size. And our output is brain weight, y. These are all the points that get plotted. When we test our model for these particular pairs of xy, all these points, xy, they form the pairs. This is the best fit line. We can plot it. Now, what about the accuracy? We know that we can consider our plotting is accurate, our prediction is accurate, if the R square value is near to 1, and it is best when it is equal to 1. So We know the R square formula is what? R square is nothing but summation of y predict minus y upon the actual y. This is the mean, sorry. So predicted y minus mean of y and actual y minus mean of y. So this is our formula. Now, this is again summation. So whatever the differences are between actual y and mean y and our predicted y and mean y. Okay, the formula is this one. So you can check the formula later on. So take the square of this, and then we're going to take the summation. So after taking the summation, we'll have our numerator upon denominator. And then this is a little different formula actually. That is why they're doing 1 minus the numerator upon denominator. And here also it should be predicted minus mean, actual minus mean. But here it is mean is there, actual value, predicted and actual value they have taken. Anyways, this is a little different formula. You can go with this particular formula also. You may get the same result. So 1 minus numerator upon denominator and print it. Now here R2 is 0.6, which is almost half of 1, right? So it is okay, but not that great a model because errors are more. Why errors are more? Because we have done this manually. This method of finding mean and doing all this is what manual method. What is the optimal method? Gradient descent, which the computer follows. That is why here the R square value is not that much close to 1. Now using sklearn also you can do it. This is very easy, in which directly the functions you will call instead of putting any formula. So how you will do it is, from sklearn, import the linear regression class. And from sklearn.metrics, import the thing that is used to find out the accuracy. Okay, like how we use R square, that there is something called as mean squared error and mean absolute error. These two things I will discuss later. What are these two? We have discussed R square. Here I am importing mean squared error. Now, this is the class. Linear regression is a class imported from the sklearn library, from the linear model part. So create an object of this class called as reg. Then reg.fit. Fit the model. That means train the model using the feature and label. And then reg.predict by giving the feature, determine the output. And then you can find out R2 score and you can print it. Okay, this is the standard way of implementing. We'll discuss more about this in the next lecture. Thank you.